In this lecture, we will continue our discussion on logical equivalence with quantifiers. Okay, so now we'll prove this formula using the earlier formula that we already have proved. Okay, so the left hand side there exist are conditional I. Okay, it can be written as there exist are not R or I. Okay, so this is the formula that we have, that is A B is equivalence with not A or B. Okay, so this formula is used here, not R or I. Okay, so this is equivalent with, okay, so let us open the bracket here. Okay, so we can open the bracket here because there is an OR operation here and there is a existential quantifier here. Okay, so it can be written as, now this negation can be taken out, so this existential quantifier will become universal quantifier, so it will become for all R or there exists I. Okay, so now this is equivalent to, we have for all R. Okay, so here we have the same formula that is used here. That is in this, from this step to this step, come across this. This is the form which is equivalent with A conditional B. Okay, so hence we have proved this one. So that is, we have there exists R conditional I is equivalent with for all R conditional there exists I, or for some I. Okay, so we just proved this one. Now come the second one. So let us prove this one in the same manner. We have for all R conditional I. Okay, so it can be written as not R disjunction I. Okay, so here the same formula that is being used here, that is A disjunction B. Okay, now we can have, let us take negation as common here, so it can be written as, let me use the square bracket here, R and negation of I. Okay, now let us take this negation out from this square bracket. So this universal quantifier will become existential quantifier. So this will be, this will be not existential quantifier. So in the bracket we have R conjunction not I. Okay, so here the De Morgan's law is being used here, so let me write down it here. So this is the De Morgan's law used here. Okay, so now this one is equivalent to, if you take it the negation outside, so this existential quantifier can go inside the bracket, so it can be written as there exists R and there exists not I. Okay, so you can prove this statement are equivalent. You can prove this one by taking some example. Okay, so these two statements are equivalent. Though this is not in the previous formula, you can prove this one. So these two statements are equivalent. So instead of this statement, I can write this statement. Okay, so now this is equivalent to we have so let me take it out this negation, so it will become universal quantifier. So it will become, so let me write it like this, all I. Okay, so let me write in the square bracket here in this way. Now use the De Morgan's law here. Okay, when you use the De Morgan's law here, so this will be not there exists R. So this conjunction will become disjunction, and this not will be cancelled out. So it will become for all I. Okay, and this is equivalent to there exists R for all I. Okay, so here the formula that is used is not A disjunction B is equivalent to A conditional B. Okay, so hence we have for all R conditional I is equivalent to there exists R conditional for all I. Okay, so hence it is proved. Come to another formula here. Okay, so in this formula we have a predicate function px and a q having no function, means q is a proposition here. Okay, and here we have a universal quantifier, so it is equivalent to this for all px conditional q is equivalent to there exists px conditional q. Okay, so we can have, so let me prove this one. So left hand side is for all px conditional q, so it can be written as not for all px or q. Okay, so this is the formula that already I have used. The same formula is used here. Okay, so it can be written as, now if I take this negation inside the parenthesis, then it will become existential quantifier. This universal quantifier will become existential quantifier. So there exists not px or q. Okay, so it can be written as, I can write it down in the bracket, in the whole bracket I can write it down here. Okay, why? Because in this q there is no bound variable. Okay, or you may say q is a proposition, there is no variable, so I can write it down in square bracket here. Whole means I can write it down the not px or negation px as well as this q in a square bracket here. So it can be written as there exists, so it is nothing but px conditional q. Okay, so let me use the square bracket here. Okay, so this is nothing but the right hand side, hence it is proved. Okay, so similarly come to the next point, fourth, how do you prove this one? So we have left hand side there exists px q. Okay, so this is similar to we have not exist px or q. So this will equivalent to for all, this existential will become universal quantifier, not px. Okay, since there is no variable here, q is a proposition having no bound variable, so we can write it down in the bracket. So we can have not px q, or we can have, so this can be written as px conditional q. Okay, so this one is nothing but right hand side. Okay, hence it is proved. Okay, so in the same manner we'll prove this one. So here we have p is a proposition having no variable here, but q is a predicate function having a bound variable x. Okay, similarly in the right hand side as well, we have p is a proposition having no bound variable, where q is a predicate function having this bound variable x. Okay, so now let us prove this one. So we can have the left hand side p conditional or for all qx. Okay, so it can be written as, we can use the same formula here, not p, or we have for all qx. Okay, so we can take it out, this universal quantifier to outside, and we can write it down in a square bracket here, because in this proposition p we have no bound variable. Okay, so it can be written as qx. Okay, so it can be written as p conditional qx, hence it is proved we have the right hand side. Okay, now come to the another formula. So we'll prove this one in the same manner. So we have in the left hand side p conditional there exists qx. It can be written as not p, or there exists qx, which is equivalent to, take it out this existential quantifier and write it down the expression in the square bracket. So we have not p or qx. So this is equivalent to p conditional qx. This is the right hand side, hence it is proved. Okay, so this much for today. Thank you.